Welcome everyone. This is session 4 of the development series in partnership with BAF, the Blockchain Acceleration Foundation, which is sort of a union of all the different blockchain organizations in different universities around the world. And this session will be presented by Boiler Blockchain at Purdue University. And it would be Kevin and Andrew. And I don't know, Dorian, if you have anything else. But yeah, good morning, everyone, or whatever you're in the world. Good night.
Yeah.
Sorry, go ahead.
No, I was just gonna say, like, good morning, everyone. Thank you for being here. My name is Dorian, also just a representative from Pagoda, which is also which is kind of like a rebrand of like Near Incorporated. So happy to be here to support and to like promote your guys' education.
All right, let's get the show on the road. So yeah, my name is Andrew. I'm a junior at Purdue, co-lead of Boiler Blockchain, and today we're going to do a little intro to the Rust programming language. So Rust is an up-and-coming language that mixes some of the best parts of languages like C and Python together into a modern programming language that's just really nice to use overall for some very important use cases. So it's up and coming in blockchain, as well as other systems programming environments. Today, we're going to go over like a basic intro to blockchain, decentralized apps, recap onto why Rust is a good idea for these sorts of applications. And then we'll go over some live programming to show the Rust specific features of this language and show like basics of why it's useful. And then we'll jump into an actual D app. So basically, blockchains are really cool innovation in recent years, and their single advantage over a centralized database is that they can allow people who are mutually distrustful to work together on something. And the obvious use case for that is money, because if there's money involved, if there's money involved, everyone has an obvious incentive to try and cheat the system. If I can convince you that I've given you money without having to actually give that money out myself, I absolutely will do so, because any rational person likes money. So that's a big difficulty with digital money. Bitcoin solved that, the double spend problem. Now, once you have digital money, you end up with digital finance or decentralized finance in the blockchain space. So this is sort of moving money around. Once you have programmable money, you can use the power of software to move that money around natively on chain. And Bitcoin had a scripting language to allow this to like a pretty basic extent. Some example Bitcoin script is here. This is what you would do to move money around on the Bitcoin chain. It says my connection is unstable. Can you guys still? You guys still hear all right?
I can hear you. Yeah.
Okay, cool. So yeah, Bitcoin allows you to do some things using its scripting language, but the scripting language on Bitcoin is really simple intentionally to minimize the attack surface. And also because Bitcoin kind of being analogous to digital gold is, it doesn't exactly place that much priority on capability. It's more so about immutability, things like that. So a few years later, we have Ethereum, which comes along and introduces Solidity, which is an object-oriented, more advanced and Turing-complete language specifically for blockchains. And you can sort of tell just by looking at this example code on the right how specific this programming language is for blockchains. Just looking at the fact that their version of the class keyword is literally the word contract. This is designed, purpose-made for smart contract programming. But we can see that with Solidity, you start to get code that looks a bit more familiar to what we would see in other languages. You have some more advanced features. You can do loops. And once you have advanced features like this, you can build more advanced contracts. For instance, voting crowdfunding, those examples that are listed in the paragraph below. So Solidity is pretty cool, but there are some issues with it that you start to run into, especially once you get more advanced decentralized apps. So for instance, this is a liquidity pool from Uniswap. And Uniswap is one of the most fundamental applications in decentralized finance. It allows you to swap tokens of any type for each other as long as someone is out there willing to provide liquidity for it. And so this example right here is just for a single liquidity pool. Uniswap has hundreds, probably thousands of these pools out there. And so Katya, a liquidity pool is basically if I have, say, Apple stock, somebody else has Tesla, or I have Near, somebody else has Bitcoin, and I want to be able to swap them for each other. I want to be able to swap them instantly without having to line up and find someone else who wants to give me the same thing in exchange for what I have. A liquidity pool, yes, there's a pool prepared. That's exactly how it works. So somebody, a third party who has both of these will put them into the pool, and then we can use the pool to exchange. So yeah, liquidity pools are a fundamental building block of decentralized finance. And it already starts to get fairly complex with these. You can imagine with more advanced DeFi applications, the software behind these apps will quickly become very complex. And because there's money involved, again, everyone has incentive to cheat the system. And the attack surface grows larger and larger the more complex this app is. So this is where Rust comes in. A lot of the exploits that happen in software apps in the wild are actually, most of them are due to memory errors. Blockchain or not, in most of these fields where they use languages like C, C++, because they have fast runtime speed, they will use these languages that are memory unsafe. Basically, like the ethos of C and C++ is we will let the developer do whatever they want. We will count on the developer to, code smart and don't introduce errors. Now, that allows you to write fast code, but it also introduces memory issues, which, for instance, buffer overflows, dangling pointers, null pointers. If anyone here has coded in C or C++ before on a fairly large project, you'll probably be familiar with a lot of these terms because they show up everywhere. And every time an error like this shows up, that's another opportunity that an attacker can exploit to use the system to their advantage. So Rust is memory safe, and that means it is impossible or difficult to run into these sorts of errors. That's because Rust will actually catch these errors before they happen. Unlike C and C++, the Rust compiler is designed to catch these memory errors at compile time. So in C++, if you have an error like this, you're going to have to basically wait until your program is running, your program is live, and you have users on it. And then suddenly you're going to realize, oh, like Bob sent money to Alice and Alice didn't get it, but we don't know what happened. You're going to have to do some, debugging out in the wild to figure out why this is happening. And debugging memory issues tends to be a very involved process. It's just a horrible time overall for everyone involved. In Rust, it won't even compile if you have a memory error there. So that's one of the great things about Rust. That's the primary advantage. And so zooming out a little bit, there are other languages that are memory safe as well, like, I don't know, Python, Java. It's harder to run into memory errors there than it is in C. But the primary difference with Rust is that it manages to be memory safe without garbage collection. So garbage collection is kind of this concept that languages like Java will use to become memory safe by basically let the programmer do what they want with the memory, but we're going to have something that runs in the background and cleans up memory as the program is running. So it's memory safe at runtime. And that adds overhead, which means these systems tend to be slower. Rust, since it does all of these things at compile time, it will do more checking at compile time to make sure that the program is fast. But once it gets to runtime, it runs as fast as C. And that's a huge advantage in applications like DeFi, where you need to be fast. So two other things that come from this are concurrency support. So concurrent programming is kind of like similar to what people call parallel programming. You can have multiple things running at the same time. Basically, that's what it comes down to. And a lot of the issues that show up in concurrent programming turn out to be ultimately because of memory errors. Now, because Rust is memory safe, that also means Rust allows you to program concurrent applications very easily. For example, it's difficult to run into things like data races or deadlocks, which are issues that can happen in concurrent programming if you're using another language. Rust will catch most of the things that cause those issues at compile time. Oh, another thing, yeah, cargo. So Rust has a Python manager called, a package manager called cargo, which allows you to install and manage dependencies very easily. If anyone has used pip in Python, it's very similar. I would argue it's almost easier than pip, but the main advantage being in other languages like C and C++, you basically don't have a package manager at all, and installing dependencies is just a pain in the ass. So cargo makes that a great time. Yeah, so cargo is similar to virtual environments. It's kind of like a combination of virtual environments and pip from Python. So it makes dependencies and all that very easy. When you have different Rust projects on your machine, you can set them up each with its own instance of cargo, basically. And how unsafe is Solidity compared to Rust? That's actually a good question. But I know that Rust emphasizes this memory safety stuff at compile time. Yeah. So let's see. Okay. Yeah, I can jump into some hands-on demonstration of some of these features now. Okay. So this is some basic Rust code, just a hands-on demo to go over some of the more Rust-specific features of the language. This is how we would do a hello world. It's the usual. Cargo run, tell it which binary to run. And then there we go, it'll print hello world. So you can have multiple binaries in one project, tell cargo which one to run, and it will run it for you. Installing dependencies, like I said, is really easy. Suppose I want to create some random numbers here. It'll tell me over here, I'm just telling it, hey, generate a random number and then print it out. If I just do this right now, it says can't find this function, and that's because I don't have the dependency. So to add that dependency, all I have to do is literally just go to this cargo.toml file and then add this one line, rand, and that alone will add the dependency for me. And now everything is fine and dandy. So I can run this. Once I've added the dependency, I can just run that binary, and there we go. It'll compile the dependencies for me. And then every time I run it now, I will get some random number. Other things, let's see, references. So references exist in languages like C as well. The interesting thing about references in Rust is this is one of the ways to see how Rust manages memory safety. You can have either one mutable reference to some underlying data, or you can have many immutable references. Now, the reason for this is so that you can't have, if you have two mutable references to the same underlying data, then one of them can change that underlying data without the other reference knowing about it. So that's how you run into things like data races or deadlocks or this data changing unexpectedly when it can be difficult to see why the data is changing. So over here, I have some underlying data, a string, and I have two references to it. If I run this right now, this is just fine. It'll print both of these strings together. If I try to make, right now, these two are immutable references, which means I cannot change the underlying data, and it's just fine. I can have as many of these as I want. If I make one of them mutable, this mute keyword is used to say that, I want to be able to change the underlying data. This is not okay, because now I have a mutable reference, and I have one mutable reference and more references. When I try to make more references to it, the underlying data, the compiler will tell me cannot borrow it as immutable because it's also borrowed as mutable elsewhere. And this is basically saying, hey, you're trying to borrow something here, but someone else already has ownership of this thing because someone else has a mutable reference to it. Every piece of data can have one owner at any time. This is Rust's concept of ownership. And in this case, since R1 has mutable ownership of the underlying data, no one else can borrow it because, yeah, so the ampersand symbol here is just a reference, which means I want S to basically refer to this underlying data. It's sort of like an alias, like allowing me to refer to it by another name, but this concept shows up in C as well. The reference itself is, yeah, if you don't use S, then I mean, then R1 will just be this string itself, sort of. It will copy that. So if you modify R1 here, it will not modify S because S, the string, implements copy, and yeah. So yeah, references themselves, like if you don't have multiple references going on, they work pretty similar to how it does in C, but the difference shows up when you try to work with multiple references in Rust, because Rust will make sure that only one mutable reference can exist. Because if you have more than one reference and one or many of them are mutable, that's where you get issues. So yeah, this is how Rust deals with references. Two other topics that I would like to cover really quick are results and options. So if you've programmed in another language like C or Java before, you probably have worked with enums. And enums exist in Rust as well, but something interesting about how Rust does enums is they have a built-in enum type called result, and they have another one called option. Each of these has two variants. For result, it can either be okay or an error. And for option, it can either be some or none. So how Rust uses this is a lot of operations that can return either something or like throw an error, or maybe they return either something or they return nothing. Instead of just directly returning the underlying thing, it will return an enum with a wrapped underlying data. And that forces you to handle the error at the source. If there is a possibility of an error occurring, then Rust will force you to handle it there so that you can't have like silent runtime issues down the road. Just for instance, with the result enum here, in this binary, I'm basically telling it, okay, divide this thing, and my division function here doesn't directly return the result. It doesn't directly return a float. It actually returns a result, which is either going to be a float or this error type that I've defined here called divide by zero error. So that's what this match statement here is doing. This match statement is also unique to Rust. It's basically saying, okay, I'm going to divide this by that. And if it is okay, then I will take the underlying quotient, the underlying data, and I will print it. And if it's an error, then I will take whatever error type it gives me, and I will print that error. So you can see right now, if I try to divide 1 by 0, that's division by 0, which is not defined. So it's going to tell me I ran into a divide by 0 error. Now, if I change this to be 1.0, something that is okay, I run it again, it's going to say, okay, that's fine. I'm going to print the quotient. So what this allows you to do, in this basic example, it might not seem like much, but a lot of Rust's built-in features will return results instead of underlying data types, because it tells you at the source, okay, there's a possibility of an error here. Tell me how you want to handle that error right now while you're coding it, instead of coming back and debugging it at runtime. Because this allows you to, for example, some error types are recoverable. Like let's say I'm the user. I put in some input to standard input, and it doesn't match any of the recognized input patterns. If it doesn't match any of those, then that's a recoverable error. I can print a message that says, hey, I don't recognize your input, try again, and then restart the function. If it's an unrecoverable error, like, I don't know how you would give it an unrecoverable error in that example, but let's say I give it something that the program just hates so much that it decides to crash. Then I can tell it, okay, if it's unrecoverable, then crash. So this also helps a lot when you have Rust functions that interface with other things that, for example, if I'm interfacing with a text file, I try to open it, it can give some errors like, the file doesn't exist. And if the file doesn't exist, I'll tell it, okay, create the file then, and then open that. So that's the result enum. Option enums are pretty similar, except instead of okay or error, the variants are some or none. So in this case, it's the same example, except I'm returning an option or something now. So now I'm telling it, if the division works, then give me an option which is some float. And if the division doesn't work, you're going to give me none. And I can match on this. I can match on this option the same way that I did with the result. If it's some, then unwrap the underlying quotient and print it. And if it's none, in this case, it doesn't tell me what error type it is. It just tells me the operation didn't return anything. So if it doesn't return anything, I'm going to print something. But basically, the point is, depending on what the output of this function is, if it's some or none, if it's okay or some error, I can unwrap the underlying thing if there is an underlying thing. In the case of none, there's not. And then I can handle it depending on what I get. So this becomes really powerful in more complex applications where you have operations that can return some number of different results. For example, it can return what you would expect it to. It can give you a couple of recoverable error types, or it can give you something that you have no idea what to do with and you have no option but to crash. So yeah, that's some of the Rust specific features of the language that we run over in very basic form. I can hand it over to Kevin now, who will go over a basic decentralized app.
Yeah. Can you guys hear me okay? Awesome. Okay, so I'm going to bring up just a quick app, and then also the code for the smart contract. And I thought it would be kind of convenient to, since we're in the scope of blockchain here, it would be convenient to look through a smart contract in order to kind of demo how Rust is used in practice. So this is a demo that's taken from near.dev. They have a lot of great examples that use Rust and assembly script, and they'll be usually pretty simple, but also are a really good demonstration for simple apps that you can build on top of to practice, since they're written obviously pretty concretely. So let's start off just from the top and see with some of the things that Rust uses. Then the first thing that we should start off with would be serialization. And the goal for serialization is to bundle your contract into a byte stream so that it can be deserialized and read when you need it to. And I like to think this a little bit like compression, so it can reduce the amount of size you're taking up, and also allow it to be readable in different contexts as well. And I think one of the things that is important to note here are these little bracketed sections here, and these are macros. So they allow the compiler to interpret those in a different way than it would typically interpret Rust code. So this first one here, you see near bindgen, and this is a near specific smart contract. And this near bindgen lets the compiler know to treat this code as a struct that's a near smart contract. And then below it, we have another macro that tells the compiler to serialize this and turn it to a byte stream. And Rust uses Borsh as their serialization tool, and it's a serialization tool that's known for safe practices and being compatible with hashing as well, so that one byte stream can't deserialize, or sorry, multiple byte streams can't deserialize into the same object, which is pretty important as we talked about in weeks past with blockchain and how hashing works. So the next thing that I think is important is that in Rust, the way that Rust tends to handle inheritance is by defining a struct first and then implementing the methods on top of it. So you can see in this contract here, we have the struct status message, and it'll define the local fields here. And then below, there are the methods that are implemented on top. And this is a little different from some other languages where you might see that the methods are implemented inside the class definition. So Rust handles that a little differently. The local variable, or the data field here is a LookupMap, which is a specific type of data storage that's used by Rust that's meant to only really look up something and not necessarily interact with it too much. And it does that for efficiency purposes because it only has to load the data that you're looking for when you want to look it up. But disadvantage, it does have a few less methods than a traditional hash map. So it's very specific, but once we run the demo, you'll kind of see why we don't really need anything more than just looking it up. So here you have a default implementation for status message. This will be really useful for testing because when you want to set up your testing environment, you can just implement the default and you'll have an environment set up a lot easier. I see a couple messages coming in. I just want to, yeah, okay, cool. And I'll go over unwrapping a little bit because they do we use it in testing in this contract as well. Oh, one other thing that is important to note is this is actually when you create a new cargo package in Rust, it'll default to main.rs. But since we're making this into a smart contract and into a struct that has methods implemented, then you'd have to change that to lib.rs to treat it as a library. So again, that's how Rust handles inheritance. Next, let's keep going down. I think this env or the n is a way to only access like smart contract specific variables. So think your account balances or account IDs or deposits, things like that. And right here, you can see actually an example of references here. So we're referencing the account ID and the message and inserting that into the record. So that's our setter. And then here's our getter, which allows us to just return the status that's associated with this account ID in the map. And that's where, when I was talking about the lookup map, that's why this is a really efficient way to implement that, because we're not really doing anything else other than just trying to get the status that's associated with that specific account ID. Okay, so if we keep moving down, we're going to start getting into the testing, which is sorted under a module, which means this isn't actually implemented unless we're trying to specifically test the contract, which makes sense because we don't really need this unless we're trying to test it. And a couple of the flags here. So the WASM32 is, or sorry, so the test macros allowed the compiler to see that we're trying to test the code here. So the similar to the nearby gen at the top that allowed the compiler to recognize it was smart contract code. This allows it to recognize as a test. Okay, so like I was saying, using the default is useful to set up the environment. So as far as testing goes, really, it breaks down into 4 steps where you set up a context for the test, and then you instantiate your struct. So like right here is where you can see it's instantiating it as the default. And then you can call your methods and assert that they're equal to what you're guessing they're going to be. And this is essentially the testing process that you'll go through. So whenever you add something to your code, that you can add a new test to it and say, hey, is this equaling what I'm thinking it's going to equal? And that's how the testing works. So flipping over to the actual application, it's a really simple app where you can literally just type a message and it will display the status down below. So if we were just going to say hello, then I can approve this transaction through my testnet wallet. And after a little bit, it'll update to hello. So it's going through that process of getting the message, referring to it, and then setting it through the LookupMap. And I would definitely encourage you guys to go through the GitHub link that we posted in the slideshow, because that has where this entire repository is set up to run this. And if you don't have a testnet account, those are also pretty easy to set up. I would just look up how to set up a near testnet account, or if there's a resource that can be posted in chat, I think that would also be useful. But this is kind of the general setup of how an app will run. And I don't want to step too much because I know we're going to be going more smart contract specific over the next couple of weeks. But I thought this would be a cool way to show in context how some of these things that Andrew was explaining in Rust are actually used. Andrew, I don't know if there's another piece of, if there's anything that you'd like to comment on this, that'd be useful, or things that you saw that.
I think that covers it for the most part. I guess to recap, the reasons why we like Rust are it is memory safe, but it is fast because it's not garbage collected. And because it's memory safe, it also allows for relatively easy concurrent programming. And it also has a package manager, cargo, which is a really nice feature that you don't have in a language like C. I think that about covers it. We looked at, basic ways that Rust forces you to handle errors at the source where they happen, so that you don't run into difficult to debug errors down the line and during runtime when your program is live. And then we looked into an actual smart contract. I think we have some time for questions. I saw there's some good discussion going on in the chat. Yeah.
This first one, Borsh, I'll bring up this link as well. But this is their website. You'll be able to read a lot more on how specifically it works. But you can see a lot of things that that Borsh tends to boast about in terms of how their serialization works are the same things that Rust also markets as their strengths. So you can see it's really focused on speed and safety, which is because we have to compile the WASM. Yeah, I think that if we go, I think I took notes. Okay, yeah. So the serialization actually is what allows it to compile to WASM. If you didn't serialize it, then it's not going to be able to be compiled to WebAssembly. Yeah. And a little bit earlier, I posted a link that was the Rust Playground, which is something you can use in your browser to test out certain Rust concepts, which is it's a really convenient tool to use if you're just trying to see how certain syntax things work in Rust, or just build something really tiny. So I'd highly recommend, if you're just trying to play around, trying to figure out how to implement certain concepts in Rust, that's a really good environment to do it in as well.
Yeah. Also, the Rust book. This link was sent earlier in the chat, but the Rust book is a great resource to learn about all of these things. It explains everything very well. Yeah, I call it the Bible sometimes. It's great.
Has anyone tried running the status message repo, either locally or some other way? Okay, yeah, there are a lot of great resources on that near.dev page that are slight variations, and they use both Rust and assembly scripts. So whether you're looking to develop in either one, there's going to be options there. And I think there are actually some of them that are the same app that are in both Rust and assembly script. I could be wrong about that. If you wanted to see how those compare as well. Yeah, I know that as the weeks progress here, it's going to keep getting even more near specific. So I don't want to step on the toes of the other presenters for the next coming weeks. I know that's going to be their bread and butter. But they do have Near has really great documentation on their entire software development kit. So if there's anything that you see that is, might look confusing, or why near tends to process things certain ways. All of it's very, very well documented.
Definitely happy to provide any resources for that. We also have just want to plug our Discord channel, put in the server. If you're working on near projects, like every day, like 11 a.m. Pacific Standard Time and 4 a.m. Pacific Standard Time. We also have like office hours that you can jump into, or I'm there at 11 a.m. Pacific Standard Time to work with you on your problems or your questions like live. Yeah, I put this in the channel. So put anything else I can find in chat that's useful.
Yeah, and I think if you're wanting to start playing around with near, one of the best ways to do it is to go through one of these apps, that's one of the examples that are given, and then just keep trying to make small modifications to either add features or improve certain parts if you want to. Like for example, I was playing around and I made a using the status message thing, I turned it into a devcon meter, analogous to defcon. So to supply the current state of urgency in a development project. So it's kind of a fun way to just implement different methods than were already written in the actual example. But it'll teach you a lot about how certain things work in a safer environment than just trying to develop your own app from the get-go, because you could run into other issues that are not there with these examples that are going to work. Oh yeah. So near SDK is the software development kit that's set up to allow smart contracts to be written for near. So it has all of the tools that you're going to need, including the serialization and setting environment variables, and even the near bindgen macro are all included in that. Yeah, here, let me grab the sorry, my E key is broken, so it's a tough time typing since it's a pretty common letter. Yeah, I know it's been tough. It either doesn't type an E or it types two at once. To make things okay. Yeah, so there's the near SDK, and there's it actually will give you a pretty good rundown of all the specific parts that you're going to see up here, just because those are used in pretty much every single smart contract, because everything has to be serialized and compatible for near smart contracts. So it's a great place to look for how those work. Did I paste that in chat? Oh no, I did. Okay. Oh, I did want to one thing that I forgot to mention. Andrew mentioned unwrap here, and it's actually used in testing as well. So it's the contract, when you get the status, it's expecting something or the value to be of a certain type, or string in this case. And when it unwraps, if it receives a none, then it'll panic, and you'll know that test case didn't work. I think there are also methods like unwrap or else that allow you to, in case it's going to panic, you can set a default value essentially for what that's going to return. Yeah. So macros are just ways for the compiler to know that certain code should be. Yeah. Cool. So it lets near know that this code here needs to be turned into something that can be put on chain. So you can't just take this code and put it straight on chain. It needs to be wrapped and bundled in a way so that it can. And that's what the macros do. They'll take the code that you wrote and it'll generate something from it so that it can be read or written in the way that it needs to be received.
Yeah, so like line 12 there on Kevin's screen, the derive macro, that's a good example of like probably the most common macro in Rust. And in this case, that macro is being used similar to the way that you might see inheritance in other languages. So the deserialize and serialize keywords there are traits, and a trait is kind of like some shared behavior that some data types can have. So this is how Rust does what most languages would call inheritance. And in this case, it happens to be through a macro.
It's used on the struct definition, and then also the method implementation as well. So anything that needs to be wrapped for like in the context of a near smart contract needs to have that macro above it so that it can be read. Oh, so you're asking why it's not above the default there? Is that, oh, did I just? I honestly, I could be wrong, but I'm pretty sure it's for the default type that might be included in the struct definition. I don't know. Andrew, do you know how that is handled there?
I mean, I don't know the specifics, but I mean, all of those, like the implementations blocks you have there are all for that struct, and the derive macro is on the struct. So I guess they just.
Yeah, like, I mean, at least for like in terms of the specific macro, yeah, it's just like used on like the struct and impl, because it's like, yeah, essentially serializing it's serializing like so you use the struct to kind of like define your state in your collections for your smart contract, and use like impl to define like methods that are going to be like called onto that struct. So like nearby gen is like essentially a way of like serializing this data to then be able to be interpreted onto the blockchain. Like I think it was Andrew mentioned like it gets serialized into like WASM. So they will like effectively allow like users to be able to interact with these methods that you've defined here in your smart contract. But like in general, like macros aren't necessarily like specific to like structs and implementations. You can like find them on like function definitions. Like I've seen them on parameters. They're just kind of like a tool from like writing like again code that produces code. So I don't know if that kind of answers your question. Also, you serialize. I mean, like here, like it's serializing like implementation. Maybe I'm not understanding the question properly. Do we? Oh, okay. I think attributes are a little bit different in Rust. Sorry, my memory on attributes is a little foggy. Yeah, I think attributes are a little bit different in Rust, but my memory on that's foggy. But like, yeah, they don't necessarily have to be like attached to that. Let me think. Yeah, that one I don't know if anyone else has an input on that particular question.
Yeah, I guess I'm not exactly sure how to answer that either, to be honest.
Yeah, that's a good question. I'm not too sure about the semantics there, but I would guess that like when you have the implementation block, it says for status message. So if it's implementing something for something which has the macro on it, then it takes all of the implementations with it. That's what I would guess is happening. But yeah, the Rust book definitely goes over this in more detail.
there's another question for like line 20. So the initialization of the LookupMap. So yeah, so essentially like what's kind of happening there is like, so LookupMap is like one of Near's collections on from the SDK, like even like Near SDK AS has like its own kind of like set of collections. I mean, they're similar, but so LookupMap is kind of like a key value pair tool. So it's like a hash map or even just like an object, you can think of it. And like essentially what's happening in kind of like line 20 is that you have to attach like a prefix to each collection you instantiate. And then the reason why you have to attach a specific prefix to these collections is so you don't like run into data collisions on the blockchain, if that makes sense. So like if they have like the same prefix, like it'll like be, I think the smart contract could like come to an error, or like it'll mess up the state of the blockchain, so it won't be able to like run properly. And like I think like if this part like like I'm gonna my brochure is like next part, but like this is also explained in your SDK.io, so I'll double check right after it says, but like so you have, but like so that BR thing, it's like a way of like serializing that like string, that like specific name for that prefix. And that's like essentially like we have to like do, so the blockchain can like read your prefix for that specific collection. And I don't know if there's an initialization function anywhere else in here, but or it might just be like default. Oh yeah, impl default for SAS message. So normally on other smart contracts, you have to like initialize like these like collections you create with a specific initialization function, but you have that impl default for SAS message, so it automatically it initializes all of these like collections for you, or this struct for you. So yeah, it's a kind of like, it's essentially what's happening there.
And I posted the link to the data storage and collections under the Near SDK, and that'll have it split up by assembly script and Rust.
And I just provide a link from the Near SDK-io on like collections and these unique prefixes. Which of the functions that you have will use up gas? So if you go down to set status on line 27, that's signaling to the Rust smart contract that this is going to be a change method. And any change method will essentially like charge a fee that you have to like pay for, and also like will essentially like use gas. I'm kind of like everything in a way like uses gas. If I'm being honest, like, so gas essentially is just like computation cost on a blockchain. So like any action you create, any data you store, any data you modify that changes the state of the blockchain, that's gonna like all use up gas. I think technically even view methods also use up gas, but like Near kind of covers that. But so like say like get status message, which is just like at self, like that's just like a reference to self. It's just pulling information from the blockchain. So yeah, it's like, say for gas and transaction fees, that won't like incur a transaction fee, for example. But yeah, like, but anything like essentially when it comes out to it, anything that like performs some sort of computation will cost gas. Like, yeah, gas is computation. I can also give you a link for that too, actually.
I think most of the things that are in the smart contract will involve computation. I think that's the kind of the goal of the contract, is to bring everything to one place that's going to actually interact on chain. And then anything that doesn't need to interact with the blockchain or that's non-computational will be put elsewhere. Do you mind? So how do I analyze large data? Yeah. So like storing data is definitely really costly, and that's why we're seeing things like IPFS being used for anything that's larger than a contract in general now, because it can get really expensive to store large things on chain, like images or videos. So storing does take gas.
Blockchains are definitely not good for large storage, that's for sure. Like if we look back to the first slide that I started with, where I said that the sole advantage of a blockchain is enabling adversarial participants to work together. That should be like at the core of all sort of blockchain thinking. It's worse than a centralized database in just about every other way. So slower, less energy efficient, costs more to store things. Yeah, if you don't have a reason for needing to collaborate adversarial participants, then you're probably better off with a centralized database.
So I might be misunderstanding the question, but are you asking how would you access past data, as in like past data on chain, or?
I hope you don't mind if I mute myself. Can you hear me?
Oh yeah.
Okay.
Yeah.
So there is actually somebody called Ben Gertzel. I'm going to post a link to his Wikipedia page. He doesn't operate on Near. I think he's connected via Solana, so I don't know what language they use. But his idea is that he has a decentralized AI, so like machine learning tasks, which can solve problems. So people can come to that decentralized network and request for a particular machine learning algorithm. And then there's some competition. The best algorithm is the one that's presented to the user. I guess they must provide the current data or like a data point, and they say, okay, look, classify this data point into, is this an image of a cat or a dog or some other task, And then the algorithm solves it and returns back the answer. But all of this is over a smart contract from what I understand, because a person then pays in the tokens for his company, AGIX. So I'm just trying to understand how something like that would work. So in a simplified version, if I just have a smart contract that wants to solve a machine learning problem, if I write this up in a typical manner on any programming language, I'll just go and write the whole thing, I'll write the whole algorithm, I'll provide the data to the algorithm, maybe I'll read a CSV file, maybe I'll connect to a database, right? So this is just like the usual programming style. But if I want to actually create a smart contract around that so that I can have people come and get a service and therefore then pay in tokens for the service and receive the answer, I don't fully understand how this would connect to a blockchain. How can I write a smart contract that can solve a task? And specifically, there are some machine learning algorithms that require the entire data set. So I can't train it offline and then load it back up, like load some parameters back up and just have access to the parameters. I actually have to have access to the entire data set. So it's probably like I don't know, maybe way too out there for this particular lesson, but since we have a couple of minutes and no one is asking questions, I just thought I'd check if you guys have any ideas on that.
Yeah, I would agree with what Liam is saying. If you don't need to perform any machine learning tasks on chain, that would probably be ideal. If you're going through that entire learning process on chain, that's going to be potentially, depending on your data set, you're talking possibly thousands, tens of thousands, millions of transactions, which would get very, very expensive very fast. So I think the part where the contract would come in is if you're trying to get maybe the results of your data that will come from the machine learning algorithm, which you should probably do off chain. I think that would be the uploading step would be where the smart contract comes in. Yeah. So I would definitely do the training online, and then if he requires you to push your data on chain, then that's where the smart contract would come in. Oh well, so yeah, I wouldn't include the original data. Probably only the stuff that you're generating. Basically, the least amount that you can put on there, the best. Because the more that's on there, the more expensive it's going to get. So anything that can be done off chain should be done off chain. Like Andrew was saying, blockchain is only really good for one thing, and if anything falls outside of that scope, it's best if you can try to keep it outside of that scope. But obviously, sometimes that can get a little complex, like you're saying.
I was thinking, so there are two scenarios. One scenario, a user can arrive and say, look, I've got my own data. I've got tons of data. I'm a big business. Here is my data. Can you find some information from it? And another scenario that could say, well, here is a data point. Use your data and give me the answer. So two scenarios. I think the scenario where they arrive with a single data point is easier, because in that scenario, like you said, let's calculate everything offline and just load up the parameters that were learned. But in the scenario where a user comes with their data, how could they actually give me the data, for example? I actually think that's probably actually not going to happen that often. People don't want to give each other data. But if it did happen, like a person arrives with their data, I guess there have to be workarounds around the contract.
Yeah, because
there's no way to do it within the contract.
Yeah, so if you were trying to upload a massive data file, obviously that would be super expensive. And one of the solutions to that is using IPFS, which I think is interplanetary file sharing. And that will allow you to pin a certain file. So you could pin your data set to this IPFS like interface, and then you'd be allowed to, in your contract, just get that file from IPFS, so that you're only interacting with usually it's just a JSON object, which takes up a lot less data than having that entire file be put on chain.
So sorry, can you explain a bit how that would work? So I arrive to your smart contract, and how do I share my data via IPFS?
Yeah, so Dorian just posted a link. This is really, really common with NFTs because it would be really expensive to put images that are several meg, or even videos that are much larger on chain. So it's a really common thing that's done with NFTs. So if you look at that example that Dorian sent, then that'll show how to pin an image to IPFS. But that process should be the same with pretty much any file type.
So feel free to ask any other questions if you have any. Maybe, yeah. Unless you have anything to say, Dorian, Kevin, or Antonio.
Yeah, like yeah, for wrapping it, like I'll say yeah, always again definitely want to like plug in some of our services for like learning near, if that's okay. Like we have like near.university, which is like a way you can like kind of like study, like get like learn your topics like on your own time, get on board into that environment. In terms of like learning Rust, like definitely would recommend like just in terms of like Rust workshop, like definitely recommend the Rust book. I mean, like I think it was mentioned a few times earlier. This is definitely mentioned a few times earlier in this call. Let's see, here we go. Rust book. Yeah, so I definitely would recommend like looking to the Rust book if you like, just like it give you like a great like overview of like all the concepts and everything you need to know to become a like a strong Rust developer. And like just for, I mean, like, and if you and like here's like another link I think is like I kind of like start off with like just like as like a small like taste into it if you want to into like Rust, but like let's see if I can find it. Yeah, well actually, yeah, I'd say like look into, yeah, this recording, yeah, I think that this video is recorded too, right? So Yeah, exactly. So yeah, I feel like this workshop like did a great job like doing overview of like kind of like what you need to know for us as well. So yeah, Dorian University, you can jump into our Discord server like going to near.chat. If you have any questions, like I'm always there. I also have like a YouTube series that like I created. Some of the tutorials are a bit outdated, but like, I can give you one that like I just created about maybe like 2 months ago for like minting NFTs. So if you guys want to check out the YouTube series for making decentralized application, that's also there for you. So I can like find the one for NFTs, but let's see. Yeah. And yeah, feel free to ping me in the Discord server if you guys ever have any questions. Like I'm always happy to answer anything that you guys might come across. If you guys want resources or development help or anything, like I'm always online most of the time. So mostly during the week. Here we go. And let's see. Oh, cool. Yeah. Yep. Yeah. And that's, I think mostly all I get. Yeah. Thank you guys for jumping in. Thank you guys for having me. I had a lot of fun here.
You're welcome. Thank you so much for coming.